Is it better or still not full?
Okay.
Okay, maybe not completely full screen. I don't know why.
Don't worry. Okay, we will see your slides.
Okay, thank you. Then let me start. Why I cannot start the... Okay, but sorry, maybe this is not completely the full screen, but let me start. Okay, anyway.
We see your slides very well.
Okay, thank you. Okay, so let me talk about the quantum computer. Okay, this is not my specialized topics. I'm a lattice field theory is my main subject. But okay, the organizer suggested maybe once to discuss about this kind of thing is not so bad. So I think probably this is my first time to talk about this subject, and probably the last time to speak this one. Okay, so I want to talk about today quantum computers, and this is my collaborators. And so collaboration is from Japan to Russia, Moscow, from Tokyo to Moscow. Okay, not so important. And about the history of the quantum computer, it's rather old, already 1980. It's a Russian, so it's a translation. So I think this is a Sovietskaya Radio Moscow. So I don't see this paper, but anyway, but almost at the same time, maybe independently, Paul Benioff, I think he's a U.S. physicist. He proposed quantum mechanical model. Okay, it means in the modern world, it's a quantum computer proposal, of course. And then Feynman, after 1 year, said simulating physics with a computer. Of course, his effect is very strong. And so in his talk, he said, I want to talk about the problem of simulating physics with computers. And okay, then more work coming from the Landauer. He was working at IBM, but he's also a physicist. So he asked, is there any limitation of the computer from the point of view of the thermodynamics? So is there possible to make computers generating no heat? And there were two answers, yes and no. So yes, there's heat for some data copy, but no for some memory reset, because if we put there is memory reset, it means we decrease the entropy. So it means, yes, usually it's accompanied by the heat anyway. These are old history. Just I read some old history. Then Paul Benioff, he proposed more realistic one, or more concretely, quantum mechanical model of the Turing machine. It essentially he is in mind the quantum computer in modern days. Then Feynman said simulating physics with computer. So of course his effect is very big, and many people started to discuss. And so, but at the beginning, okay, I will. It's a quite application were quite limited, but I think nowadays we can calculate even hadron masses that this is my main research topics. We can do in the quantum computers, although still we need many trials. So okay, just continuation. History of the quantum computers. And Peter Shor, he's also, I think, a physicist. But anyway, mathematician. He presented the factoring, but of course, a big numbers factoring is very time consuming. And but this is important because modern cryptography depends. Big numbers factorization is very difficult. So if there is some good way to solve this factorization in a second, then modern days, cryptograph was many systems does not work. So, but anyway, these are why information people are quite interested in these topics. But for us, rather, what Feynman said, simulating physics with computer, he published the paper here, but in 1982. This is, I think, interesting for us here. So this is just a terminology, just we can say, and it does not solve anything. But in this field, quite often people are talking about the quantum supremacy. This means simply quantum computer is faster than classical computer. If such a quantum computer, if we have this kind of quantum computers, we can say, okay, now we have reached the quantum supremacy. And sometimes some companies, some people said, okay, now we achieved this quantum supremacy. So some programmable quantum computer can solve a problem that no classical computer can solve in any feasible amount of time, not a million years or something like that, but some and not some trivial problem, but a really useful problem. Then, if this is achieved, then quantum supremacy is satisfied, people say. And at the beginning, quite important contribution is Yuri Ivanovich Manin. He, in his book, he showed or the idea of this quantum computer. So I think now we can say Yuri Ivanovich Manin was or is one of the first to propose the idea of quantum computer already in 1980. And in his book, I think this is unfortunately, not unfortunately, sorry, in Russian, so I cannot read, but anyway, this is his book. And in this book, he proposed this idea, I mean, the quantum computer's idea. And nowadays, there exists quantum computer hardware. This is the Chinese companies, and this is Canadian companies, and okay, this is IBM Q system. Of course, IBM is very strong company. So now this machine, not so many in the world, but maybe more than half are IBM Q system 1. I asked also in Japan, please buy this one, but yeah, the university still is not, still doubting. But anyway, so this is a computer. So we should express bit, I mean, 0 and 1. And in IBM quantum computer, so is based on this superconducting qubit. This is qubit is essentially bit, but in the quantum bit. So this includes this one. And this is the also, I think, American NIST, National Institute of Standard and Technology. They also developed ion trap, using ion trap to describe 0 and 1 for quantum computing already 2011. And I think this is also Chinese company, semiconductors method to express quantum bit. And also photonic is also proposed. These are, yes, I think Chinese companies are quite aggressive in this field. So I cannot access these, but anyway, just I read their announcement and papers and so on. Okay, and already several progress, and in United States, so this is essentially IBM's quantum computers. So I don't know if he understood or not, but anyway, he visited and he looked and he said, "Oh wow," or something like that. And this is the Google quantum computers. This already more than, not more than around 10 or 20 are already sold. And of course, also Russian built a laboratory for developing quantum artificial intelligence. I've never been there, but Russian Quantum Center, there is such, and quite similar to this previous IBM one. But okay, they are very similar, but this part is essentially cooling system. So essential part is around here. And in Russian railway companies, also they introduced quantum technology. Just I read in some news, Russian railway plan to extend trunk quantum network to Sochi, Ekaterinburg, cherry beans. I'm sorry, I cannot. But anyway, so why railway company? But the Russian railway company will build this quantum network in around these regions. And so they are testing and basis of some cluster in Moscow. And Europe, CERN, not announced, but encouraged quantum computing and quantum simulations, quantum sensing and communication. CERN proposed or encouraged countries to attack this problem. And Italy is always part of the CERN, but a bit independent. But so they are now doing this kind of trials. And China is, as I said, China is very aggressive in this field. Already 2 universities, and this is University of Science and Technology. Some from point of view of the technology big universities, I heard, yes, my daughter 2 years ago visited here and she was quite impressed. And yes, so they published already in 2 papers, as far as I checked, 2 papers in Physical Review Letters, a strong quantum computational advantage, and Gaussian boson sampling. This is a famous some algorithm, but anyway. And Japan. And they quite recently, Fujitsu company and RIKEN developed superconducting quantum compiler at RIKEN. And I asked if I can use, and they said, please wait. And after several months, I got no answer. Okay. And so here, related with our high energy physics, I checked several related references. So this paper is Hot QCD is the American US company, not company, I mean US big group. So multi-GPU lattice code for QCD and lattice gauge theories on quantum computers and quantum simulation for high energy physics. And I think this is also US groups, variational quantum algorithm, and their name is Japanese-like, but I think they, IBM people, quantum random number generator. I think this is, for example, in newspaper, these are quite, big topics, but this is not so, big, but I think for us, at least for me, this is quite important because for numerical simulation, random numbers are quite important. So I'm very impressed they are doing such a basic research using how to use quantum computers. And this is also quite recent one. So they try to write this is essentially to write a code showing a model. Of course, showing a model is a very simple but fundamental field theory model. So on quantum computers, they try to write this one. So these papers are quite useful, at least for me and probably for you. And so then how to use quantum computers? There are, of course, hundreds of possibilities, so you can find many good ones. One is just during my group. Theoretical, nuclear physics. At least one of my friends said, still delta baryon is 3 quarks or nucleon plus pion some deep bound state. And but to judge, of course, okay, we calculate the lattice and check and comparing with experiment, we can get some answer. But to get the answer, really, we need very high quality lattice calculation. So this is just some speculation or dream. If we have a quantum computer and very high calculation of these quantity and comparing with experiment, we hope we can get the answer for that. And so about that, of course, we need experimental data, but not LHC or something very high energy, but rather low energy, because we want to study the detail of hadron behaviors. And so Nika and JPAC, of course, and they are not so high energy. And I don't know the detail of Nika, but at least I have several friends in JPAC. It's a Japanese accelerator. They said, okay, our accelerator energy is not so high, but instead we try to, indeed, they look the very high intensity beam and very good measurement system. I cannot judge, but anyway, maybe you can judge better than I. But so then it's useful to, they said they want to study hadron behavior in detail. Then this is when we have a quantum computer, maybe we can really collaborate. Okay, this is not so important, but anyway, this is the JPAC, Japan Proton Accelerator Research Complex, JPAC. I don't know how to pronounce Nika or Nika. Well, yeah, and it's a Russian near Moscow. I don't know. Nucleotron-based ion collider, Nika. Okay, so these I expect they produce good experimental data. And okay, my friend Osaka at Osaka University. So we discussed what we should do, or if we can access these quantum computers. So he proposed maybe it's good to start strange hadrons, because probably we cannot calculate a very huge lattice because of the money and machine. So, but here many interesting research subjects. We thought, okay, strange hadron is already solved, but okay, we can calculate the mass, but if we want to see the detail, he's at least according to him, it's not. So if really we can calculate these strange hadron, baryon, and meson, and very precise, very fine lattice, very high statistic, maybe we can get some interesting theoretical result. And we hope, yes, if there is a new data from the quantum computer, and indeed, at least in Japan, this JPAG people said, okay, one of the big our target is strange hadron, they said, and the detail. And some simple question is delta baryon is 3 quark, or this is the old questions. And this occurs also for S quark sector. So N star 1531. This is the similar situation. This is the this is considered as a bound state, but this L equals 0 and so on. Okay, you can check these things, and to analyze the detail, these are quite important fact. So okay, but anyway, so now K meson are measured in JPAC and Nika, and these are high population of the K, and these are just JPAC energy region and Nika energy regions, and so probably we can do interesting things. So suppose we can get machine or GPU time of the quantum computer. So what is the interesting new topics? Okay, just this is one possibility. One is real-time simulation. In lattice theory, usually, of course, it's a imaginary time Euclidean calculation, but there is a real-time simulation was proposed, but it's cost too much, and usually we don't do, but maybe we can do again. And also, Hamiltonian lattice was once studied, but this really we should calculate eigenvalue and eigenstate of a big Hamiltonian. So this is now for many years it's people give up to apply. But if we have quantum computers, maybe, of course, not so easy, but we can challenge. Okay, so okay, now I come to conclusion. So our possible next research subject is strange hadrons. And so if we have a chance to use quantum computer, really we can get a very decisive achievement, we hope. But at this moment, at least our collaboration, Japan and Vladivostok Moscow collaboration has no chance to use quantum computers. But there is a famous statement by Martin Luther King. So just like that, if you cannot use a quantum computer, then make a quantum computers. And indeed, I asked several friends, but they said what they considered, just I'm joking. But anyway, so if you cannot make a quantum computer, use a simulator for writing a program. And after writing a program, and if we can show this is possible to do something interesting calculation, then maybe. And so these are references, these are doctor thesis, quantum simulation, and also, this is also PhD dissertation. PhD dissertation is nice because they write very detailed, very clearly. So, so just this is quantum computers is a new topic. So these two ladies really, at least maybe more, but I found these two theses. It's a good, because there is still no definite book, so this thesis is a good source if one can study. And also, there is already quantum simulation for high energy physics, and lattice-gate theory for quantum computers. This is also US group. And okay, there is such a book. And so just this is the discussion within group, but maybe first we try 2+1 dynamical simulation and hadronic observable with a strangeness, and and so on. Just we discuss what we should do. And okay, there is also some review articles. So possible target is if this is a strange hadron, okay, strange meson, baryon, and many things. And so today I do not have time to discuss at least these important topics, which are usually some fundamental topics: quantum Fourier transformation, Grover's algorithm, but yes, so just you can, if you are interested, please check later. You can easily find in the just in the literature these things. Okay, that's all. Thank you.
Thank you, Atsushi. Okay. Questions? Vladimir?
The question, what do you think if there is some promise in space or possibility to search or to investigate or to study multi-quarks in the framework of lattice?
Yes. Yes. And multi-quark is, of course, you mean for example, dibaryon or something like that, or the pentaquark was 6. And of course, we should be careful. Usually, multi-quark states are expected to bigger than the standard one, and so we should prepare big size lattice. I mean, maybe 100 to the 4th or something like that. And but if we have quantum computers, we can overcome this problem. And so, yes, of course, that's a quite interesting research topics. Yes.
With the size large enough, it's possible. Thank you. Thank you.
Yes.
Okay.
Maybe I ask a short question. As far as I know, there are now attempts to use quantum systems with more than 2 states, so-called qubits or qubits with D number of states instead of qubits. So, maybe you can comment what are the basic problems with this with using these states, because as I know, qubits, for example, some papers this year that qubits are even more stable than qubits. No, maybe I'm wrong.
No, I don't think so. But it's difficult to judge other groups these technical details. The best is I will try to do even the smaller system. I will try to do. Then I can understand which part is really difficult and so on. So I think that is just like a big experiment. So you cannot. Of course, it's not secret, but it's impossible to know the detail of the other groups' experimental situation, I think, unless you are a member of this one. So, of course, discussion among different groups are quite important, yes.
Okay, thank you.
Tell me, please, do you need actual universal programmable quantum computer to calculate the inner structure of hadrons, or some more simple and specialized devices like more universal quantum simulator will be sufficient for this?
I think depends. I'm not so good. Yeah, at least I cannot construct the quantum computer by myself. So for me, if there is some situation, some places where I can use even this is any kind of quantum computers, that should be at the beginning. It was announced, estimated more than 1,000 times faster, and so of course it's a realistic case. But even if I have 100 times faster computers comparing with the modern days supercomputer, I can do many. Of course, also memory is important. But anyway, I'm sorry. Maybe this is not the answer which really you want to know. But
Okay, more questions? Atsushi, thank you very much.
okay, thank you.
Let's continue